axt times the normal vector xt. This is my only. Of course, it looks simple, but the thing is that the normal vector is kind of like implicitly hidden within that. Okay, so now I'm going to look at this and I'm going to derive a PD for the U, for the level set. Yeah. So you see, looking back there, I have gamma t is basically the place where I have u xt is equal to 0. Okay. So I think in terms of multivariate calculus, I think we can compute that n, the normal velocity at any point, let's say for x in gamma t, n at x is nothing but it is du of xt over du of xt. So that's my normal velocity. Okay, I'll assume if it's smooth nothing is degenerate, this one is modified, assume anything you want. Okay. So I have that. So that means I can write this one as axt times du xt over du xt. That's something like that. Now looking back at my motion, the xt always stay in the level set of gamma t. So what does that mean? That means I have furthermore I have u xt t is always equal to 0, so it's some kind of conserved quantity, right? Because I'm always surfing on the 0 level set. So u is always 0. Okay, now assume everything is smooth again, differentiate with respect to t. So d over dt of the whole quantity is 0, right? It's 0. So if I differentiate with respect to t, if I differentiate the first law, I'm going to end up with du xt t dot with x prime of t, x dot of t, plus I differentiate on the second slot, I just end up with the same thing, ut xt t is equal to 0. So that's sort of my PDE. Okay, now I have x dot t is equal to this, so if I plug it back, I'm going to have ut plus du dot with a du over du is equal to 0. Okay, so one of the du cancel out. So eventually I end up with this PD ut plus ax du is equal to 0. So this is okay, so that's sort of cool. Now, if you, I mean, there are a lot of models, you know, but for example, now if you were to assume that the normal velocity is equal to the mean curvature at that point, at that point. Okay, don't ask me much about geometry and that, but anyway, let's assume that the velocity at this point is equal to the mean curvature of the surface at this point. Then actually you can really have the rule is x0 is equal to y and x dot of t is equal to just the normal vector as equal to xt. And the mean curvature can be written as a diversion of the normal vector times the normal vector. In other words, you have the normal vector field. Okay? So you measure the change. You take the gradient of the normal vector, and then you take the chase. It's going to give you the total, the summation of all principal curvature, which is diversion, which is mean curvature. So if you were to have this, and you know, again, this is diversion of du over du times du over du. Okay, if you plug it back into the PDE, you're going to have the mean curvature flow equation. Ut equals to du diversion of du over du. So this is mean curvature flow equation. It's a fancy object. In terms of level set method, it was by advanced probe and chain Gigagotto at the same time independently? Okay. Yeah.
Normal was equal to mean curvature is the chance of
Yeah, okay. We assume that the surface is moving with this normal velocity equal to this. It's an assumption. Yeah. It's like bubble. Actually, I didn't learn a lot, but I learned once with my daughter. It's actually kind of interesting. But that's just a motivation. Okay, so of course there's no Hamiltonian or Hamilton-Jacobi there, but at least you see some sort of like equation. We don't do anything stupid. We consider something that has some meaning. Okay, so now let's go into the theory. Of course, when you have such an equation, the first thing you will study is well closeness, right? So the first question for every PDE is well closeness. Okay, that means we care about existence, we care about uniqueness, and we care about stability in general. Actually, this was the main object in the past, way few centuries ago, and then it was sort of like also an object in optimal control theory in the 50s, 1950s, and stuff like that. And so on and so forth. So this was actually the main object in the development of viscosity solution that people are interested in the 1980s, early 1980s PDM. We don't have any problem with existence actually. Well, after some uniqueness and stability is a problem. Okay, let me give you one example. A very simple example. This is the following. Okay, consider my Hamilton-Jacobi equation of this form. U prime of x equal to 1 in just the 0, 1. And I have U0 equal to U1 equal to 0. See? Right? So the length of the derivative is 1. And then I have 0 initial condition. Boundary condition. Can you tell me what solution you have in mind? Yeah, right. The velocity, u prime is 1, so if you go up, the slopes will be 1 or minus 1, right? So okay, so 0, 1. So surely this should be a solution. Wow. This solves the problem almost everywhere. Because I have, it's only breakdown here, right? It's 1 here, minus 1 here, so absolute value is equal to 1. Can you give me any other solution? Yeah, anything is fine, right? Just very good. Like example, this is also a solution. Going down is a solution in some sense. Okay. I have to be careful. You can design infinitely many solutions in the sense of almost everywhere. Okay. So there exists infinitely many solutions in the almost everywhere sense. Meaning that it's a solution, it's nice almost everywhere except at the breakdown point when u prime is not continuous, right? U is still continuous, but it's, you can design it. Right? Okay, so it's a problem, right? Because it just, we have way too many solutions. Which one is the correct one? Or can we have some kind of selection procedure to choose a correct one? So by the way, I forgot, but I should mention that viscosity solution for Hamilton-Jacobi equation is kind of some equivalent notion of entropy solution in conservation law. In conservation law. So that means that in the almost everywhere sense we have many solutions. But viscosity solution is a theory that somehow helps you to select the correct solution, the one. That we can kind of select the correct physical solution whatsoever that means. Okay, so that's sort of like the question. Okay, so now how do we start? We see that we have a lot of solutions. So how to start? How to start this? One person this question. How to kind of unit this question in your mind? So meaning that in the almost everywhere sense is not good enough, right? You have to impose some further conditions, some physical conditions. So in order to select a solution. And maybe you can guess the name is viscosity solution, so it's going to concern some viscosity. And actually, I'm lucky because actually David already mentioned something about that. So Evans in the early 70s, okay, he looked at this question and then he thinks, okay, why don't we kind of do it in like fluid mechanics or physical way? Why don't we look at some kind of approximation procedure and we pass the limit, maybe it's going to give us some correct solution. So we consider something like vanishing viscosity approach. Vanishing viscosity approach. Which is that we not going to look at the normal Hamilton-Jacobi equation, but we're going to look at so we're going to put some smoothing effects, some viscosity effects, or some rounding motion, depending on how you call it. So you're going to look at, this is a usual equation you have in your mind, okay? Why don't we add some smoothing effects? So smoothing effect is some Laplacian. Because, if you have the Laplacian, it's not the original equation